Good morning. I think I want to start today with playing a video. Yesterday I went out to school and did some little kind of mini experiments with capacitors, and I thought I would show you that because it's usually the way I start the class with capacitors is just by having students experiment with them, and I wasn't able to do that this year. So I have the sound muted on this video, and I'll just sort of narrate it and describe what's going on. So let's see, I need to share the screen over there. Just go to screen 2. And hopefully now you see a power supply and a light bulb there that's lit up. So I'll kind of describe what's going on. And if you don't, holler. Anyway, I've got this light bulb hooked up to a power supply that's set at 5.4 volts. And I did that just to kind of figure out what I would need to light the light bulb up in a nice visible way. And now I'm taking a capacitor and I'm going to charge it to 5.4 volts as well. And I had to do a little bit of monkeying around with the wires to get it to work very well. The first one I tried had something soldered in it. I don't know what it had been used for. I think I loaned it to a chemistry student and it came back that way. But, or that was the alligator clip that had that on there. But anyway, with this blue capacitor that I stuck on there, it charged almost instantly, like just in seconds, or maybe less than seconds, maybe less than 1 second. But once I had it up there, I was able to hook it up to the light bulb. Then I disconnected it from the power supply, which I'll do shortly here. And sorry if the hands get in the way. When I took my camera out to school, I usually have a wide angle lens on it, and the wide angle lens weighs too much for the little dinky tripod I had out at school, so I had to put on a narrow angle lens. Although at times it produces very nice things. So I'm going to hook up the light bulb to the charged capacitor. Whoops, what am I doing here? Oh, I think I just talked over part of it. Let me back up here. There, that was it. The capacitor did light the light bulb for not very long. And so now I'm going to try to hook up a pair of capacitors instead. And I'm connecting the pair of them to the power supply. I'll kind of drag it through here so I speed it up. And I don't know if I stuck a third one in there or not. Yeah, it looks like I'm doing a third one. And so a trio of them I'm charging up, and I'm connecting them in such a way that they'll each have a potential difference across them of 5.4 volts. And so, and they don't take very long to charge up either. And so as soon as that's the case, then I can connect them to the light bulb. And the light bulb stayed lit a longer time. Still not a huge amount of time, but I don't know if that went right by. As soon as I get this thing okay, soon I'll have the thing connected. There we go. All right, the light bulb stayed lit for a somewhat longer time there. So these three capacitors were each, I think, 25,000 microfarads. And I connected them in such a way that the capacitance added, and we'll talk about that here shortly. The next thing I do is put in a different capacitor, a single capacitor, but it's one that has a capacitance of 100,000 microfarads. And these are big, chunky capacitors. That's kind of the way they used to be. Whoops, I must have gone right by using the light from that one. I did, and you can't read what I was talking about anyway. So there we go. There's the lit capacitor. So it did stay on longer with the 100,000 microfarad capacitor than it did with the 25,000 microfarad capacitors. By the way, something that happens with capacitors is their capacitance is given in either microfarads or picofarads or just plain farads. You don't deal with anything like millifarads or nanofarads or anything like that. And I don't know why that's the case. It's just something that has worked out. It may be because a lot of times capacitors are so small that you couldn't write the capacitances on them in any way if you had a whole bunch of different units on there. So often they'll only have the numbers on them, and that's just part of the characteristics of the things. Okay, I'm going to drag through here now. I think the next capacitor I use here is one of a different design, and that little thing has a 1 farad capacitance. So it would be 10 times the capacitance of that tall silver one. Something you give up, though, is that tall silver one, I think, could be charged to 25 volts, something like that. I'm not positive. And this one, the little one, can only be charged to 5.5 volts. And if you go beyond that, the electric field between the effective plates of the capacitor becomes great enough to arc through the material between the plates, which is called a dielectric, by the way. So anyway, I charged it up here. I'm going to connect it to the light bulb soon. I must have been talking a lot here. Okay, we'll play this and see what happens here. Okay, so now the light bulb is staying on for a relatively long time, and kind of impressive anyway. So you can see the capacitor can act as an energy storage device. And that's something that we're going to be looking at today, is how long they last as energy storage devices. Okay, the light bulb's getting dimmer now. It's in the blurry foreground here. Sorry about that. Then I took and charged one of these capacitors, but I actually put, let's see, 2 of them in series. And the reason that I did that is that these capacitors, the black capacitor there, has a maximum capacitance of only, or maximum charge on it of 2.7 volts. And by putting 2 of them in series, I was able to have the potential difference across each one be 2.7 volts and still get a reasonably large capacitance out of this thing. But it took a long time to charge it, and I actually went and answered some email and did some other things while I was waiting for that. And I'll show you the video. It probably took 15 minutes to charge it. So that's what I had to wait for. And now I'm going to have to mute this again because it was fairly loud. So this is after 15 minutes or something like this. Audio mute. Okay, now I can play it.
Okay.
Whoops, I thought I muted it.
I actually went away and did.
Yeah, so now I've got these two capacitors in series, and I don't know if I have it written on there, but actually I'll show you in a minute. I've got a copy of their ad. It looks like 500 farads, so lots of capacitance on these things, just kind of an amazing amount. And the light bulb's going to stay on for a long time with this. In fact, I ended up cleaning up the lab, getting a bunch of other stuff out that I had to film for my Physics 114 class. And I was ready to go, and the light bulb was still lit. So I ended up just shorting out the capacitors to discharge them because it was probably 15 minutes that it stayed lit with the capacitors that were charged that way. So they're potentially an energy storage device, and 500 farads is a lot. Those things have only become possible with some new materials that have been made in just the last couple of decades, and that's how they managed to make that extremely high. There is no longer an air gap between the plates of a capacitor. Remember, it was inversely proportional to the separation of the plates. The smaller you can make that, the higher the capacitance can be. So if you can shrink that air gap down to a millionth of a meter, which you could with a very thin plastic or Teflon film or something like that, then you can increase the capacitance by a factor of 1,000,000. And if it's flexible, then you can end up rolling the stuff up. And here I was trying to show you what the capacitance was. But it did take a long time to charge it, though, and mainly because the power supply couldn't deliver a whole lot of energy. But today we're going to look at just how much energy would have been stored in that capacitor and learn about the energy that is stored in them. So I'm going to get out of here. I don't know that I've even had my IPEVO on today, but drag that over here and hopefully it's still visible. Let's see, I want to, oops. Oh well, it's in focus now, so maybe I'll leave it that way. I want to go on to manual focus and lock it. Okay. That way when I'm waving my hand, it never focuses on my hand. Okay, the one on the bottom is the black capacitor that I had there. And I think I was able to pay less than $6.89 a piece for them, $6.89. I think I got a package of 3 of them for $15, and I got about 3 packages of those in the hope that students would be able to experiment with them this year, and that's not happening. The thing above it is something that can be charged to a higher voltage, but you probably can't see it, but I was looking at the capacitors themselves, and each of them is a 2.7 volt capacitor. And so if you connect them in series, you can have those 6 capacitors there charged to 6 times 2.7, which ends up being 16.2 volts. So they just round it to the nearest volt there. And it's a 58 farad combination because you've got 6 capacitors, excuse me, each of 350 farads. But it turns out when you connect them in series, their capacitances add kind of like, let's see, we haven't done resistors in series and parallel, I don't think. But anyway, we'll take a look.
We did in the lab.
We did in a lab. Okay, that's right, this week's lab. Yeah, capacitors in series add like resistors in parallel, and capacitors in parallel add like resistors in series. So kind of an interesting thing about them. I don't remember how much that thing on top happened to be, but you could make your own if you wanted to, although it's kind of nice having this all hooked together because you wouldn't have to do any connecting with a whole string of wires or anything like that. And you could store quite a bit of energy, as we'll see. So let's first talk about the capacitors in series and parallel and see just why they add the way they do. So we'll just sort of do this with pictures, I guess. If we think of the parallel plate model of the capacitor, by the way, the electrical symbol for a capacitor is that. And so when you're drawing circuits, you may have picked this up in the lab for this week, or was it last week? I don't remember. Anyway, that's the circuit or the symbol for a resistor. I may have gotten the right number of bumps on there. I can't remember. But anyway, that's what a resistor looks like. That's the thing for a capacitor. So it's just a small drawing of a parallel plate capacitor. Sometimes you'll see variations on that. Let's see. I can't remember if that's the correct one or if it's this that's the correct one. This one's not so common. That's more common. Sometimes you'll see one of these things with a little arrow across it. And what that can mean is that it's a variable capacitor. And something that used to have variable capacitors in it were the tuners on old radios. And I can remember when I was a kid, my family had this huge radio. It was probably 4 feet high, and most of the space inside it was for these monster speakers that I had in it, that it had in it, although it wasn't particularly loud. But at the back, you could just look right in and see all the electrical components. And I remember being fascinated by that. And you could see this variable capacitor. It was a thing with a whole bunch of parallel plates in it. And then between those parallel plates, there was a part of a dial that could go into there. And these parallel plates weren't a full circle. And these things were all part of a device that could be rotated within the other ones and provide parallel or variable capacitance. And a lot of electrical noise would have been produced in a device like that, especially because it was just open to the air. And so this thing could collect dust all the time as well. But let's imagine that we have a capacitor here, and I'll just call C1 whatever the capacitance of that thing is. And then I have another capacitor over here, C2, and I connect these things in parallel. And that means to make it so that one side of each of these things has the connected by a wire like that. And so these would be at the same potential, and the bottom plates would also be at the same potential here. And we can hook this up to some kind of a battery or a sequence of batteries. Whoops, didn't go down far enough. Anyway, ignore that line. So we've got delta V here is what these things are charged up to. Okay, well, delta V across each capacitor is going to be the same one. And if you remember that the capacitance is equal to the amount of charge stored in the presence of that potential difference, in this case, I'll have the potential difference across each capacitor being the same. And so I'll have something like this. I'll have delta V, which is what the potential difference is going to equal Q1 over C1. And delta V is also going to equal Q2 over C2. Now, the charge on C1 is it'll have Q1 on the top plate and minus Q1 on the bottom plate. C2 will have Q2 on the top plate and minus Q2 on the bottom plate. But the total charge stored in the presence of that potential difference is going to be Q1 plus Q2. And in that case, the effective capacitance, C effective, will be the total charge stored, Q1 plus Q2 over delta V, okay, which is Q1 over delta V plus Q2 over delta V. Okay. Well, this is C1 and this is C2. So when you connect capacitors in parallel, the effective capacitance is just the sum of the two. Now, when I was playing around with those blue capacitors, the bright blue one, I connected 3 of those in parallel, and the effective capacitance became C1 plus C2 plus C3. They were each about 25,000 microfarads. Turns out there's a lot of variation on capacitors, actually much greater than there is with resistors. But I would have had an effective capacitance with those 3 in parallel that would have been about 75,000 microfarads. So would have had that. In series, something else happens. And if you're connecting capacitors in series, okay, so let's suppose that we have over here a battery, and it's got a potential difference across it of delta V. So if you hook up a voltmeter to it, you get that showing up. And here we've got C1, C2, and C3 over there for our 3 capacitors that are in series now. And so on C1, we'll have some amount of charge Q1 on the top plate and minus Q1 on the plate there. On C2, we'll have a charge Q2 on the top plate and minus Q2 on the bottom plate, and same with this one, Q3 minus Q3. But here's the deal. If I make a dashed line around this thing, there is no electrical connection between these parts and the outside world, in effect, and the same with these parts in the outside world. There isn't any electrical connection between the plates of the capacitor. And so what that means is any charge that shows up on the top plate of this one, the Q2, had to have come from the bottom plate of this one. And so what you end up with is Q1 equals Q2, and same thing happens down here. Whatever charge you get on Q3 had to have come from here. Now, really, it's the negative charges that do the moving. So the negative charges here had to come from here, which was initially neutral. And so Q2 equals Q3 as well. And so you end up with the same charge on every capacitor, even though you've got this string of them in series. Your net charge that's stored in the presence of this potential difference that you've got, this battery that you've got hooked up, is the same as if you had a single capacitor. And let's see if we can figure out how that's going to work. Well, just starting off, C1 is going to equal Q1 over delta V1 where if you could hook up a voltmeter across this capacitor and see what the potential difference is, then you'd have something similar for C2. C2 is going to equal Q2 over delta V2. Actually, I may as well just call these Q because they're all the same. And C3 is going to equal, I'm going to cross out the subscripts on these because it's just some charge Q, but the same on all of them, delta V3. And let's see what I end up with in this case. If I solve each of these things for delta V 1, 2, or 3, I would get delta V1 is going to equal Q over C1, and delta V2 is same Q over C2, and same with delta V3. Delta V3 is Q over C3. The sum of those delta V's is going to equal that delta V. So delta V1 plus delta V2 plus delta V3 is just equal to the total potential difference across this thing. The effective capacitance, C effective, is going to equal the Q that we have, however much charge we have, divided by that total potential difference. And let's see, what can I end up with on that? I guess I could write this as Q over delta V1 plus delta V2 plus delta V3, which end up being, kind of a messy thing here. Let's see. Q over C1 plus Q over C2 plus Q over C3, which ends up being Q on top, Q over C1 plus Q over C2 plus Q over C3. And this is easier to write. The Q's all go away, and you end up with 1 over C1 plus 1 over C2 plus 1 over C3. And if you play around with this, it turns out that 1 over C effective is equal to 1 over C1 plus 1 over C2 plus 1 over C3. And that's the same as the formula for resistors in parallel. And that's why capacitors in series happen to behave that way. There's probably a more efficient way to come at this than what I did, but that works anyway. So that's capacitors in series and parallel, and that, wherever they went, this picture of the bank of capacitors, these capacitors would be in series, and that was the formula for capacitors in series we just did. Anyway, these would be in series, and so you end up with the effective capacitance, if they're identical, 350 farad capacitors. The effective capacitance is 1 over C effective is 1 over 350 plus 1 over 350 dot, 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 dot. It ends up being 6 over 350, but then when you flip it, the effective capacitance is 350 divided by 6. So that's where you get a net capacitance of 58 instead of 350. And they just round it to the nearest farad there. Again, these are things that are not all that precisely measured. Like if it says 350 on there, it could be anywhere from, I don't know, 340 to 360, and they'd still call it good. And maybe if they're outside that range, instead of throwing them away, they sell them cheap. So They can do things like that. Now, what about the energy stored in the capacitor? I talked about that a little bit and wanted to kind of go through that idea and grab some paper here. The idea that we'll start with is that we imagine there's a bunch of different ways we could do this, but one is to imagine taking a little chunk of charge dq here, just dq, and we're going to move it across this thing. And this will be the upper plate, and it'll have a charge up there of that's going to be positive somehow. And then we'll have negative charge down here. And we're going to be moving it against an electric field that points downward because it points from the positive thing down to the lower. Now, some things that we can do with this, we're going to assume a parallel plate capacitor. It just keeps the geometry simpler. At the tail end of section, whatever chapter we're in, 21, 22, 23 or 24, I lost track, but they do the mathematics for a spherical capacitor and a cylindrical capacitor. And I'm not going to bother to redo those calculations, but you should read that so you're familiar with the results of those. I think some of the homework I put up has questions about those. But we'll just assume a parallel plate capacitor here where the capacitance is epsilon naught A divided by D. And also with parallel plates like this, the electric field that's in there is going to equal, well, actually the potential difference at any time, delta V, will equal the electric field strength times D. And so there's another relation. And then let's see, God, am I going to have to use Gauss's law again to get this thing? The electric field is equal to, let's see, I can never remember this expression. Need scratch paper. Let's see, infinite plane, Gaussian surface. Let's see, integral of E dot n hat dA, which turns into just E times A is going to equal the charge enclosed over epsilon, which is sigma A over epsilon naught. There we go. Okay, the electric field that's in here is going to equal sigma over epsilon naught when I've got a conducting thing up there, as I do. So that's the electric field. And sigma will equal the amount of charge per unit area. So I can combine all of these things together and try and figure this out. Now, how much work do I have to do to move a charge dq across that electric field? Well, the force on the little bit of work is going to equal dq times E times the distance that I have to move it. This will be the force on that charge, and the distance that I move it is going to be the separation between the plates, which is D. So ED/dq is what it ends up being. Now, I have to keep in mind that E is going to equal the amount of charge that's already on there divided by A. And so this will look like, I'm going to rearrange things here. I'll have D times the amount of charge that's on it divided by A. Whoops, and epsilon naught. I've got that down here. Almost lost it. Okay, Yeah, if you take Q over A and replace it for sigma here, you end up with Q over epsilon naught A. Okay, well, this I think is equal to D over A epsilon naught. That ends up being Q over the capacitance of this particular device. Remember, the capacitance is epsilon naught A over D. So that C goes on the bottom there. So that's a little bit of work. Well, what about to charge that up to some final amount, capital Q? How much will that look like? So the total work then, where did dq go? I lost it. I forgot to write it down. Okay, the work is going to be the integral from not having any charge on there to having some final charge Q of Q over C dq, which the 1 over C can come out front, and I'll integrate from 0 to Q there. That'll be 1/2 Q squared evaluated at 0 on my final charge, or it ends up being 1/2 the total charge stored on there divided by C. Okay, well, we can write this a whole bunch of different ways. Often we don't know what the charge Q on there is, and we don't bother to calculate it because it's not particularly useful. But with knowing this expression, Q over delta V, I can replace that Q with C delta V, and then the work to charge that thing, which ends up being the energy stored in the thing, is going to become 1/2 C squared delta V squared over C, or 1/2 delta V squared over, whoops, C delta V squared is what it ends up being. Sorry. C delta V squared. So that's one way that you can write that. And that'll be the energy stored in the capacitor. So it goes up with the square of the potential difference across it. You usually don't see the delta on there. And so it would just be the energy stored is 1/2 CV squared. And that V represents the potential difference across the capacitor. You can also write that in other ways, I guess, but that's a way that's kind of nice for us. A few years ago, I remember seeing in the Moses Lake paper, actually it's been a long time ago, like maybe 10 or 11 or 12 years even. I know we were discussing it at a band practice one night with some guys I played music with that I didn't start playing with till 2008. So it must have been sometime after 2008. But there was an article in the paper about these huge capacitors that they were installing out by REC Silicon. And what they were for was to store energy so that it would maintain the voltage to their industrial setup if there was ever a power outage, and it would maintain the voltage and allow them to keep running those things until diesel powered generators could be brought online. They could not afford to have the industrial process they had going there to manufacture silicone lose voltage for even the briefest of times. And so they had these huge capacitors. And I wish I had saved that article to find out, or because it mentioned just how large the capacitors were. And they were like the size of a 55-gallon drum or something like that, if I remember seeing the picture of it right. And so I don't know how many farads those would have been, but that would have been kind of neat to see something like that. One time I went down to WSU with we used to have a tour that would go down there in the fall and sometimes in the spring and visit their engineering program. And part of it would always be going around to visit some of their engineering student clubs. And they had one that made electric powered vehicles. And the one year that I remember, they showed us what they were using in their vehicle instead of batteries, and it was big capacitors. And these were things that were about the size of a pop can, and they had, oh man, I don't know how many dozen of them that were underneath. They're a lot lighter than a lead acid battery, and that's what they were storing the energy in. And I know there's been some research into using capacitors for potential energy storage devices in electric cars, but I haven't heard recently about how that's gone. I think most of them are still using some form of a battery and not capacitors. Okay, well, let's finally try some problems today, if I can remember where in the world I put them. That's all just plain white paper. That's projectile motion. I think they're on the back of here. Oh, did I not print these off since I expanded them? Looks like I didn't. I've got to be able to read those problems. Okay, that's a bigger font. Well, actually, I don't know how many pages this file is. Oh well, just go to print. I'll just do current page one at a time. Oh, and then we'll do that problem. I hope I'm on the same current page or a different current page. Anyway, suppose we have two capacitors connected in parallel, so their capacitances are going to add across a 300 volt potential difference. Calculate the energy stored in the capacitors. So these would be some kind of capacitors that can handle high voltages. And if I recall, those Pepsi can sized ones could handle a high voltage. So the energy stored in these things is going to be 1/2 C effective times.
I think you need to switch to the IP vote.
Oops. Yeah, actually, I just need to get this file out of the way. If I could move it. Yeah. Oh well, file close. Oh, I better save it first and then do it. File close. Now I've got word in the way. Okay, are you seeing it now?
We can see it now.
Okay. Anyway, the energy is going to be 1/2 C effective times V squared. And because these are in parallel, you just add those two things together. And so the effective capacitance will be 6.0. Now, microfarads are times 10 to the minus 6th. Oh, something else that'll drive you crazy about the way farads are written. A microfarad capacitor, what you'll often see written on them is MFD with a capital M. So it's not a micro symbol, it's a capital M, which in the metric system could mean mega. But I don't know that anybody's ever made a megafarad capacitor or not. That would be pretty unusual. But anyway, this is how it's going to work. And then, let's see, we'll have 300 volts squared. Now, unit-wise, remember a farad is a coulomb per volt. And so we'll have coulombs per volt that comes from the farad. And then we've got volts squared here. And so we'll end up with coulomb volts. But a volt is a joule per coulomb. And so this will be coulombs times joules per coulomb, which are just joules. So yes, this does have units of energy. And doesn't sound like much energy. 0.5 times 6 EE minus 6 times, we should be able to do this in our heads just about, 0.27 joules. Okay, that's not actually very much energy. If you remember way back fall quarter when we introduced the idea of energy, to show you how much a joule was, I took a 100 gram mass, which is, I would guess that the mass of these two batteries is probably close to 100 grams. And I dropped it from a 1 meter height onto my foot. Oh, no, we never got to meet live. Okay, so we didn't get to do that. But if you take a 100 gram mass and drop it 1 meter, it will have a kinetic energy of 1 joule when it hits your foot. Well, this thing's only got about a fourth of a joule. And so that's not very much energy. What if you had them connected in series instead? Well, in that case, you would have E is going to equal 1/2 times the effective capacitance, which ends up being 1 divided by 1 over 6.0. Oh, wait, that's not right. 1 over 2.0 microfarads plus 1 over 4.0 microfarads. And you'll have to do some fancy monkeying around here. Let's see, get a common denominator. It'd be 4 times 2, I'd have 6. I'd end up having I don't know if I can pull this off in my head or not, but I think I can. Or let's just do that in on our calculator. 1 divided by 2 plus 1 divided by 4 is that. And then I have to take the reciprocal of that. I can raise it to the -1, and I get 4/3 of a microfarad out of this thing. So and again, that'll come out joules. So let's see, that looks like 2/3 of a microfarad. 1/2 times 4/3 is 2/3. So 0.67. Not much. 6. Let's call it 6.0 times 10 to the -2 joules. And so, and you charged it all the way up to 300 volts. So not much energy to be had there. Yeah, that one wasn't terribly exciting. Okay, there's a last thing for today. I want to talk about, we figured out that energy stored in a capacitor was 1/2 CV squared when we had that. Let's look at the energy density between the plates of that capacitor. And so, oh, that's probably an inconvenient letter to use. Maybe we'll call it U for the energy stored in the capacitor, because E I want to use for the electric field. And it is in the electric field that that energy ends up being stored in the capacitor. And so it's not necessarily thought of as in the charge that's on the top plate or the charge that's on the bottom plate, but actually the electric field that exists between the plates is where that energy ends up being stored. And so I want to try and get something for that now. Let's see. The electric field strength is sigma over epsilon naught. So that's something that I want to use here. The capacitance is epsilon naught A over D. And the potential difference ends up being ED, E times D. And remember, that gets squared. So we've got all kinds of stuff going on here. Let's see, 1/2 CV squared, let's see, becomes 1/2 epsilon naught A over D times E squared D squared. And still have an epsilon naught there. I get epsilon naught A D E squared. Okay. AD is the volume of this region right here in the capacitor. And so that's kind of neat. Energy per unit volume ends up being this. And this shows up in other areas of physics as well, but or you can come at this from other ways. But for us, this will be our first introduction to this expression, that the energy per unit volume in an electric field is 1/2 epsilon naught times the strength of the electric field squared. And you can store energy in electric fields. You can also store it in magnetic fields too. So this is our first view of that. And I forget what letter we use for that. It might be a lowercase sigma, but I don't remember. Oh well. But how much energy is stored in a cubic meter due to the fair weather electric field of 150 volts per meter? This is just it's not a very strong electric field, but it's one that just exists in the air. And so, well, 1 meter is usually our typical unit volume, but let's see what it is. See what the units come out to here. 1/2 epsilon naught is 8.85 times 10 to the minus 12th. Now it's Newton meter squared per Coulomb squared. It's Coulomb squared per Newton meter squared, are the units on that. And then the electric field, which is 150 volts per meter. Okay, but we have to figure out some stuff here. A volt is a joule per Coulomb. And somewhere in here, these electric problems get worse and worse on the units. So I'll have volts squared per meter here, but a volt is a joule per coulomb. So this would be coulomb squared per Newton meters cubed, actually. And that volt squared here is a joule per coulomb, but it's a joule squared per coulomb squared. And let's see, the coulombs go away. Joule squared per Newton meter. That was a Newton meter cubed. This isn't coming out quite right for me. Maybe it will. Oh, wait. That would have been a meter squared down there. Okay, now we're good. If I think of that as a Newton meter times a meter cubed, this Newton meter is a joule. Yeah, I end up with joules per meter cubed for units here. So that makes sense. So with that electric, that electric field strength, we'll end up with a particular amount. Not much, but a little bit anyway. Yeah, I get about 9 point, yeah, we've only got 2 sig figs as far as I know. So actually about 10 times 10 to the minus 7th joules per cubic meter. Okay. Wait, 10 times 10 to the minus 8th, excuse me, which is 1 times 10 to the minus 7th. So each cubic meter has 1 times 10 to the minus 7th joules of energy stored in its electric field. But if you imagine how many cubic meters you might have, like say in a football stadium that's enclosed or something like that, that could amount to a fair amount of electrical energy, but getting it is another matter. Anyway, some new ideas: energy per unit volume stored in an electric field, and that's kind of a neat expression for that. It's sort of like energy stored in a spring, 1/2 kx squared, or things like that. But we'll stop there, do some more playing with this stuff tomorrow, and tomorrow will be about our end day for capacitance, and I think we'll be able to have a review for the test on Thursday. So, okay, how do I unshare? There we go. Okay, any questions pop up on those things or any other stuff? This week's lab will be resistivity. It's resistivity is related to resistance, like density is measured to mass. The resistivity is a microscopic property of material like copper or silver or alloys, things like that. And when you take that material and make it into some particular geometric shape, then you get a particular resistance for that device. And resistance is going to depend on what it's made of, which is where resistivity shows up. And that's what you'll be doing in this lab, is determining the resistivity of, let's see, some copper and also an alloy that I do not know what it is. It just says NS wire, and that's a very vague definition, but it's just this week making a couple of graphs and filling out a worksheet on that, and then probably doing a little bit of search. Wikipedia should work pretty well from it for that to compare it to the accepted value for copper, at least. The NS wire, we have no idea. It's an alloy of some sort, but we don't know what the particular blend happens to be. So I used to think it was nickel silver, but I don't think that's right. If it was, it would be NAG, I'm guessing, but maybe not. All right, we'll stop there and I'll see you tomorrow.